Oh, excuse me. Ah. Good morning. All right. Yeah. Well, got to wait 103. 103. Just doing a volume check. I am on a new device, but it worked for the morning classes, so we'll just hopefully go with this. Will still work here. Okay, that light needs to be solid. Yep. All right. Do. Good morning, folks. 6 seconds here, just doing a quick volume check. You may notice if you have the camera angle, I got a thing in the mail, one of these like headphones slash microphone combination things, because the old microphone I was using, it does not pick up very well, so I was speaking very loudly. I was slouching into the microphone. I thought it just makes more sense to get a thing like this. So I hope that the volume levels are okay. At least they were for my morning classes. Let me know if you have a complaint about volume too loud, too quiet. I will do what I can, but I'm actually noticed, at least for my morning classes, I could just talk at a normal-ish volume instead of basically shouting, which I had been doing for the last week and a half. So I think this will overall help me keep my voice a little bit. Just the reminders, quiz was the quizzes are officially dated for Tuesdays, but recognizing we've got all sort of different schedules, the quiz is due Wednesday. So if you did not turn it in yesterday, that was the intent. Just turn it in by the end of the day today. Do look at the next quiz study guide already. In fact, the homework that people are getting a little stuck on here and there, I mean, that's natural. Please drop by office hours and ask your questions. But one of the ways to get unstuck is to please make use of the next quiz study guide. There's a response due today, right? Due today, due Wednesday as. And actually, all the responses for the rest of the semester, I already posted those. They're available on Canvas. Some of them might not make complete sense yet, so you might want to hold off. But like, if you want to get something going, you got a little time, go ahead and do that. I am sorry for being behind on grading. The submission of some things in Canvas, both for this class and for calculus, it's changing up how I need to grade things, and I'm figuring out parts of Canvas that I never use. So I'm sorry about the major delay. I'm going to try to do what I can over the next couple of days and lose sleep and grade and whatever. This is a new normal in terms of the workload. Things I'm spending more time doing things, not less, actually. So sorry about that. I'll try to get around to things as quickly as possible here. And then just a reminder, please, homework is due Thursday. always think about starting these as quick as possible. If it's due on a Thursday, as it has been all semester, sometimes people get in this habit of, I know you've got your other classes, but you don't want to start looking at it on a Tuesday, right? Just 2 days before, you like want to turn in the one this Thursday, and I haven't written next Thursday's yet. That's on my list for today. But like as soon as you turn in the one that's due on Thursday, tomorrow, you want to start thinking about the next one. Look at it right away because it'll already deal with the things that we're doing in class, that we've been already doing in class. Okay. We're still in section 4.8. We're on day number 3 out of 6 on functions. Let me change the pen thickness here. So just the key definition, right, was let A and B be sets. By using a capital A and a capital B, this is saying you can have the same set. A could equal B, or you could have different sets. A could be different from B. One could be a subset of the other. They could be completely disjoint. Anything can happen. A function f from A to B is a binary relation from A to B, satisfying two properties. I'll write the two properties in the same traditional way, but every day I'm trying to just give a new interpretation, new words to it. So for all things in domain, there exists a thing in codomain such that ordered pair AB belongs to F. If instead of ordered pair AB belongs to F, you wrote F of A equals B, I'm fine with that. But the quantifiers matter. I mean, I think with a homework question that's coming up, people are noticing that quantifiers matter. So whenever there's quantifiers, they're not just there just because. They matter. If you don't have them when stating a definition, it's not correct. If you're missing them as you're working on a proof, things don't work out as well, so please be careful about those sorts of things. Next one, for all A in domain, for all B in codomain, for all C in codomain. If ordered pair AB belongs to F and ordered pair AC belongs to F, then ordered pair, then just B is equal to C. Okay, and just to let's just include this, that A is domain. We call, what happened? There we go. Sorry. We call A the domain and B the codomain. So written a little differently than yesterday, a little shorthandy. There's the definition, and I just want to comment that part 1 is trying to talk about this idea that, I mean, it's really a for all, but so I'm being a little informal. But if you have a thingy that belongs to capital A, then A must appear as the first coordinate of an ordered pair in F. That is what is trying to be communicated. Of course, the second coordinate has to belong to capital B because we're talking about a subset of A Cartesian B. So it's sort of automatic that it has to belong to B, but we're just including that there exists B in capital B for emphasis, and because whenever we've written down quantifiers, we've mentioned what set the thing comes from anyway. The second part, so when you have an element A in capital A, then there shouldn't be two ordered pairs. There shouldn't. I mean, it's written as an if-then. Part 2 is written as an if, triple for all and then an if-then. And that if-then language works because the grammar of conjunction, disjunction, and implication, like everything can be written in this language. It's great that everything can be written in that language, but to just put some more casual language to it right now, there shouldn't be two ordered pairs in F with the same first coordinate and different second coordinate. It's basically what part two of the definition is trying to say, just in the formal language of this, right? So if ordered pair AB is an F and ordered pair AC is an F, the only way that happens, again, here with the matching A's, it is critical here that there's an A as the first coordinate in both places. It is the same A. Then this, it's written as an if then, but it's like this forces, right? This causality, this implication that then it has to be the case that B is equal to C. Okay, and then, always stick with the habit of, is this a set that's not a relation, or is this a set that is a relation but not a function, or is this all three? Is this, whenever you deal with a thing, is it all three? Is it a set, relation, and a function? These are things to always keep track of. Please don't do this process. I know I said it yesterday, but people think continuous function equals function, and that's not true, right? So get it out of your mindset that like you got only things that can be drawn or something like this. I mean, you'll see in an upcoming response that in fact one of the domains I have in a response question I want you to look at, domain for a certain function, is just diamonds, clubs. Oh goodness, can I even draw clubs? I tried. Hearts, spades. The four. Ugh. Don't laugh. I mean, you can laugh if you want. I can't hear you. Um, that ends up being the domain of a function that I introduce in one of the upcoming responses in a week or two. So what would we even mean by continuous function? Like, where are you going to plot these things on your x-axis, I guess, if that's the domain, right? So like a lot of the baggage that comes from all of the domains in the past for functions from calculus used to always be a certain subset of the reals. Like, you got to let go of some of those sorts of things. Like, I mean, it's helpful that we say vertical line test, but we're being kind of informal to just connect the real deal to the past. We had the notation F colon A arrow B as just a quick shorthand to say that you've got a function f with domain A and codomain B. And then one other bit of notation. I know, so we had like f of s is equal to t. It's more familiar function notation. We had ordered pair st in f. That's the thing that goes back to sort of the official original way of stating what the definition of function was. It reminds you that a function is a special kind of relation. And of course, yesterday we introduced a new notation, s maps to t. You can only use this if the name of the function, if there's only one function in the problem. You don't want any ambiguity. To review definitions from yesterday in a sort of brief fashion, so let's stick with f as a function from a to b. If the ordered pair st belongs to the function, so is this ordered pair is an element of the relation, then t is the image of s, and s is a preimage of t. And you may recall yesterday's conversation that the use of the words the and this grammatical are actually the most appropriate words to put in these two places. The other thing that we did that you all practiced, I hope, I gave you some sort of awkward pause time to work on it, was if you have a subset, I'll call it capital S, of the domain set, here I guess the domain is, well not I guess, the domain was capital A, then the image of S under F, so that was new phrase defined yesterday, is, and the notation looks a little funky because it looks like we're applying f to a set, but it's just notation. I mean, why not this notation? So, and it was as you run through each little s in capital S, you apply f to little s, and those are the elements of this set. I guess it's not in here today to say it this way, but I'll just even though it's not in the notes, I'll just mention. We also talked about range, and it turns out, just to state it a new way, even though we said it an officially different way yesterday, but based on this image of S under F, we could say that the range of F is actually it's a f of which subset of capital A? Well, it's the whole freaking thing, right? So written like this f of capital A, I'm saying plug in for the capital S over in the previous definition, plug in a capital A. So I hope that looks okay as sort of the briefest of reviews of yesterday. Yesterday, right at in the last couple minutes, I mentioned this warning, and this one, it's like I last time I taught the class, I said this warning, like 4 class days in a row, and people still. So sorry if this is a little annoying, but I want you to understand that there's a difference between f versus f of x. So let's just go with if you've got a function, the discussion here, just to make sure, is if you have a function f, let's say a is a domain, b is a codomain, and let's just go with you've got a specific little x belonging to capital A. If that's your setup, f, this thingy over there, is a set, is a relation, so it's eventually a set. Okay, and then f of x, this thingy, is not a set. It is an element of capital B. Is an element of capital B. So this, let me just box the two for comparison. Just the letter f by itself, it is our notation or our label for the function, and that function is eventually a relation. That relation is eventually a set. Okay, so this is the function. Is a function. This is an output of that function, right? So think about I guess a specific analogy would be, think about the function sine of x. So sin is typically the name of the function. So sometimes your function name is not a single letter. From trig, that sometimes it's 3 letters long. And then when you apply sine to the angle pi over 2, you get the number 1, right? So what's boxed there, this f of x, if x had been pi over 2, then f of x would have been the number 1. So in what world would you say that sine of x, this function that has this graph that looks like this wave, it's periodic, is the same as the number 1? Right? Those are not the same. This idea of f versus f of x comes up in the definition we ended class with yesterday. Today's goal is to look at this definition and essentially just one other definition, and to really play with the ideas and examples, non-examples, all the usual business. So here's the definition we ended class on yesterday. Let f be a function from a to b. So a is domain, b is codomain. We say f is injective. So some books prefer the phrase injective. Other books prefer the phrase one-to-one. I'm going to ask that you get familiar with both words. If, remember the first if in a definition really operates like an if and only if. If for all x and y in the domain, if f of x equals f of y, then x is equal to y. Okay. I want to practice the usual kind of things to think about. Is whenever you see a new definition, I want it to be like your instinct, your habit every single time is to ask yourself, what part of speech? Do we have a noun? Do we have an adjective? Do we have a verb? You should ask yourself this all the time. Of course, in this case, what we have is an adjective, right? If you had a noun, then there's always a second question to always ask yourself if you have a noun. Like if you have a noun, you should ask, do I have a proposition then? Or do I have a set or a relation or a function? Ask yourself which of those, be as specific as possible, you have. But if you have an adjective, there's always a question you should ask as well. It's what kind of noun can this adjective apply to? Because it's always in math, it always is just one thing. It's whatever the definition says. In this case, notice that injective is an adjective that applies to f, and the first sentence clarifies that f is a function. Even though the word function wasn't used, the notation of f colon a arrow b is saying, little f is a function. Okay, so injective only applies to a function. I've seen people, like by the end of the semester in this class, trying to apply injective to a relation, but if the relation isn't a function, the word doesn't apply. I've seen people try to use injective on an equation. Just because there's two equations floating around here, can't do that either. So really the word can only apply to, it's an adjective that only applies to functions. I should comment that this definition is written in other books a different way. So there's even the definition that's written up here, you could write this differently. And please don't try to memorize this thing word for word. We're going to talk about how to think about this in a moment. But I'll just comment that just to word it differently, maybe another book might actually mention the word function by writing down the 8-letter word. Might do something like this: the function f from x to y. So you don't have to stick to capital A and B. You could use x and y. You could use B and C or whatever, right? Like, so two separate labels for the domain and codomain is injective. If now the quantifier stuff needs to stay, right? So if you miss the quantifiers, it's at some point, in just a week or just in the next homework, you're going to be expected to prove that a certain function I give you is injective. You're going to be expected to use that some other function I give you is injective. So you will need to use and you'll need to prove. And if you miss the quantifiers in front, it's going to be a problem. So we're going to include the quantifiers here. Okay, for all x and y not in capital A though, huh? It's got to be capital X now, right? So 2 universal quantifications to the domain. Then the text, the thing that I really want to change up is this if-then text, because you could totally write it like that, but you could take the contrapositive. Remember, the contrapositive of an implication is identical. I mean, it's logically equivalent. So you can replace one for the other and not change the meaning. Not for the converse, but for the contrapositive. So if, so we write if, and then it's negate the conclusion from before. So if x not equal to y, then f of x is not equal to f of y. Okay. So I want you to just stare at one version of the definition or the other and think about what's going on here. Like over here, this is saying, whenever you've got 2 things in the domain, if the 2 things in the domain, you just didn't accidentally pick the same thing twice, so they are different things, little x and little y are different things from the domain, then when you apply f, you're going to get different outputs. Does that sound fair for what that's trying to suggest? I mean, I want you to process, like what's being said here. Like, it's not just to stare at this and treat this all as a bunch of notation. Like, think about how the version in green in the original definition stated. So if you pick any 2 things, x and y, in the domain capital A, so that's the for all part, let's say you have the property that the outputs are the same, then the inputs are the same. I want you to think about that, right? So if the outputs are the same, that forces the inputs to be the same, right? And in fact, that's the way to think about this. Like, I mean, we'll dig into some examples in a moment, but the point is, sometimes, I don't mean to rant too much, but like, sometimes people get in the habit of trying to memorize the definition of injective as, okay, so starting after this if, people try to memorize it like 1, 2, 3, maybe 4, then 5, 6, 7, 8, 9, 10, 11, 12, 13 pieces. That's ridiculous, right? Like, I don't want, definitions are not to be memorized word for word. There's a complete lack of understanding of what's going on. I want you to, there's no way that you're going to memorize, when we have 2 definitions a day, what's going on by doing that. And there's no intuition then for like attacking a proof in doing that. Instead, I want you to see here this general idea that I had of when you have 2 things from the domain, if the outputs are equal, it forces the inputs to be equal. It's that kind of language that I want you to try to to bring out from this. And I want you to what's the word here? I want you to, when you stare at a definition, not just in this class, not just for the rest of the semester, but like in the next math class that requires 225, that's the habit you should try to get into. Is you read a definition, you sit there, and before even looking at the author's examples in a book, you want to go like, huh, I wonder what this is talking about, and then try to bring up those interpretations, like, implication being a force, like implies, right? That's the kind of thing I want you to think about. At home, I think it's important to try it. So like this, the text after the first if is what defines things, right? Think about negate and then simplify for all x, y in A. If f of x equals f of y, then x equals y. Yeah, think about how to negate this, because you see above underlined in black the definition of injective, but then if you negate, you'll get the definition of not injective, right? So remember, negating a for all as there exists. At some point, you've got to convert the implication. De Morgan's rule will apply. That's all I'm going to say about this right now. Just as a note, if I ask you if you get stuck on things in office hours and I ask what's the definition, what's it mean? What's it mean for f to be injective? It's, I guess, technically an answer if you answer, oh, that means f is 1-to-1. You're not wrong if you say that. It's just not maybe all that helpful, right? The point is, if f is injective, the text I want you to bring up is something that looks like that, for instance, or the one below, but like what's in that blue box, that's what you should be bringing up. And by the way, because this first if in a definition is an if and only if, I don't want to, folks, keep reinventing the wheel every single definition in every single class. If you need to prove f is injective, then you need to prove what's in the blue box, meaning you got to go back to connect it. Like these are the puzzle pieces I want to connect together, right? Like we talked about how to prove a for all a long time ago, but if you've got to prove a function is injective, you're proving what's in the blue. You're proving the statement in the blue box. If you need to use f is injective, then you got to use the statement in the blue box. To use a double for all, well, you're going to need two things that belong to that set capital A, right? So that, in some sense, this is what we do for almost the entirety of the rest of the semester. We do spend a little time in some other chapter where we don't do proofs for a little bit. But the rest of the semester, this is the story, like with these definitions of like, it's just picking apart like a word like injective and then translating into like what's in the blue box. And then that's how the proofs go, right? So we're always going back to like, how do you prove and use a prove versus use a for all, or how do you prove versus use an if then, how do you prove versus use of there exists. All the stuff from the past all applies. But before doing any proofs, I think what we should do is, staring at this definition, we should look at some examples and non-examples. It helps, I think, build intuition for what's going on. So first example, I've got a function f. I didn't name the capital A and B separately just because it'll take extra time. So my domain set is the set 1, 2, 3. My codomain set is 4, 5, 6, 7. Look at this function defined by f is equal to the following set of ordered pairs. So I've got 1, 4, 2, 5, and ordered pair 3, 6. This, I just now finished defining the function. This function is injective. So take a look at the text in the blue box. See if it seems to apply. So I want you to imagine this for all. We're not going to do a formal proof of this right now. I just want you to think about like simulating what a proof would look like. So for all x, y in capital A, meaning capital A in this example is the set 1, 2, 3. So imagine you have like 3 index cards. You wrote a 1, a 2, and a 3 on the 3 separate index cards. You put them inside a bag, and then without looking, you just randomly pull out one of the cards. That's X. Now put that card back in the pile. so in the basket you still have the three cards that say one says one says two, one says three. Then pull out a card at random and call that one Y. So that's your for all X in A, for all Y in A. Then is the implication true? In other words, if you look at the output of X and the output of Y, either they're going to be equal or not. Now, if they are not equal, then your implication's already true. Remember, the definition of implication stated that if the if part is false, then the implication's automatically true, regardless of the conclusion. So then you can move on. Now, if the outputs of X and Y are equal, then you got to check, is X equal to Y, right? Over here. And if that happens, cool, repeat the experiment in your mind. I think every time this experiment works. The point is, if the outputs are the same, you are thinking about the same input. As a non-example, well, maybe I'll pause. Sorry. How's that? Let's just wait for a good 10 seconds, see how we're doing so far. Okay, I'll go with we're doing okay then. As a non-example, I'll follow the just because we just used F. I'll use a G. Domain 1, 2, 3. Codomain is the same set as the previous function, so set 4, 5, 6, 7, and this will be defined by G is ordered pair 1, 4, and then the ordered pair 2, 5, and then the ordered pair 3, 4. So this I've now fully defined a function called G. This function it's a function, it's just not injective. Not injective. So both f and g are functions, but g is not injective, and this is because this for all, whatever statement is false. Take a look, because g of 1 equals g of 3. After all, both of those are a 4. Both outputs are 4, but 1 is not equal to 3. So how do we feel about, just from the first example and first non-example, how do we feel about injective and non-injective? Questions, thoughts, comments, especially comments? Have you seen this in a previous mathematical class? Somebody's got to have a good comment about this. I bet there's some ideas brewing in people's minds. Have you seen this before? Okay, I guess I will then challenge you to think of, oh, wait, I saw this. Okay, saw this in linear algebra. Okay, good point. It comes up directly in linear algebra, depending on what slant is taken to teach it. Okay, so it does come up directly in linear algebra. I'm thinking even earlier in your math career. I know I'm trying to dig in the past. Thanks for that comment. It does come up in linear algebra, but I'm thinking about like even before taking calculus, maybe in pre-calculus. I'll let you think about it. I won't reveal any answer right away. I'll just horizontal line test is what I see. That was the comment I was hoping to hear about. Yeah. So again, this is the geometric view. It only works if you've got a function from reals to reals. So it's not perfect, of course, because we have functions that have like a set of all card suits and whatever. But like, yeah. So 1-to-1, at least for the functions that are from reals to reals, corresponds to the horizontal line test happens. So vertical line test is a thing you need for a function. The horizontal line test is a thing that happens in addition for a 1-to-1 function. Again, that's if you could draw the graph of the function. All right, so thanks for those comments. Okay, we did sort that out. Because we're gonna need it for a moment, and normally on the board I'd be able to point, I'm not going to copy paste that. That's messy. I'm going to just rewrite. Let's recall the key thing that was written in blue over there was for all well, I'll just f. This is come on, pen. This is all right. So let's just recall that f from a to b is injective. This is a little less formal, right? If for all, I need some letters. C and D. I don't know. C and D in the domain set. Capital A. So if the outputs are the same, the inputs are the same. So f of c equals f of d implies c is equal to d. Okay, so cool. It was messy. I was going to copy paste from earlier, but there was too much drawing on top of that. What I'd like to do right now is do a very short proof for you. So prove that the function f from domain is set of all integers, codomain is set of all reals, defined by f of n is equal to 2n minus 1. So up to this much, the text that is underlined in green is what defines a function completely: domain, codomain, and rule. This time around, the rule is given in a more familiar fashion by a formula, but that's not required, right? Like you saw in the non-example that I can still point to up here in green, I never gave a formula, I just told you the ordered pairs, right? So these are two different ways of describing functions. Anyway, I need to finish writing the statement. So there's a function completely defined in green. The rest of this question is to prove that this function defined this way is one-to-one. Of course, if you just replace the word one-to-one with the word injective, same problem, right? Same exercise. So in answer to this question, we'll take a look. Notice in this box here, this is my essentially copy of definition. I might be using different letters than earlier, but hey, placeholder variables anyway. If you need to prove, and this is the general point of the class, if you need to prove this, you need to prove f is injective, you need to prove this. So remember the first if is really like an if and only if. So the text that is in the two red boxes, the way I'm thinking about this as a mathematician, and this is what I want you to be thinking about, is the two boxes are completely interchangeable. So if you're proving what's in one red box, you're proving what's in the other red box. If you're going to use what's in one red box, you're using what's in the other red box. So I hope that helps really kind of set the stage for like what I'm talking about of all the things of how to prove versus use a for all and a there exists and all, like that's all we're doing. We're just the next several weeks is just more excuse to practice this stuff. So we need to prove a thing that starts for all two things in the domain, right? I mean, in our official definition, we used a capital A, but here the domain is E. So we should let two things belong to the domain. So you don't have to use the same letters, right? You could use a C and D, you could use an A and B, you could use an X and Y, whatever letters, right? And then we want to show if, I got to replace the C's and D's in the box with A's and B's now. If f of A equals f of B, whoa, where's my, whoops, I see. If f of A equals f of B, then A is equal to B, right? So I know I'm demonstrating this, but I want this to be like, it's just, I hope the processes we're doing right now are not so surprising. Now, if we would need to prove this implication, let's assume the first part and prove the second part, right? So suppose, or assume, or let, first part, f of A equals f of B. And if you want to write the want to show to help remind you, go for it. We want to show A is equal to B. So how are we going to show A is equal to B? Well, take a look. We have, because of this, I know it's just 2 sentences ago, but I'm going to just write it right now. Since f of A equals f of B, let's look at how we defined f. It's underlined in green, and now we need to apply the rule part. We are told that f of a thingy is always 2 times that thingy minus 1. So what we're going to do is the left side of the equation over here says f of A. So I'm going to replace f of A with 2a minus 1. The right side of the equation, I'm just rewriting the entire equation, but like so the right side of the equation says f of b, and so after the equal sign, we're going to replace the f of b on the right side with a 2b minus 1. Maybe it helps you out to see it if I just write it directly underneath, but I don't want it to look too procedural either. So I did not do something to both sides of the equation. I didn't like add to both sides of the equation. What I did was I replaced f of a with 2a minus 1, and I replaced the right side, which said f of b, back to what's circled in blue with a 2b minus 1. I just don't want to write it directly underneath because I think that looks a little too much like college algebra class. So I'm trying to make it as part of a sentence is all. So cool, we have this equation, and now let's apply algebra techniques. So let's add 1 to both sides. You don't even need to say by adding 1 to both sides. That's maybe a little too much. So adding 1 to both sides, we have 2a is equal to 2b. Dividing both sides by 2, so we get a is equal to b, and that was the conclusion we needed, right? Back here in circled in blue, our want to show was a is equal to b. So we're done. We've proved that this function defined in green is injective. Okay, I would like to look at the other major definition of the day is function f from a to b is the setup. We say f is surjective, or the other word that you can use is onto. If for all b in B, there exists an A in A such that ordered pair AB belongs to F. Did I write it that way, or did I use the f of A equals B? I used the f of A equals B. I'll copy my notes. Either way is fine. Such that f of A is equal to B. Okay. So all the usual deals. Look, the new term, I mean, there's two different words that could be used, but they're completely interchangeable, but they're both adjectives. And this adjective only applies to functions. I remember one time, I think when I taught linear algebra last, the word onto came up because that's what the authors of the linear algebra book we use prefer. And it was a really interesting thing. Somebody was like, onto, I thought that was a preposition. You know, like preposition meaning like above, below, to the right of, in front of. And onto in normal English is used as a preposition. Used as it is in a math class, it's not. This word is actually an adjective, which is unfortunate, but that's just how it is. So warning. So, I mean, I think the point of saying that is sometimes we bring a little too much of our intuition of a specific spoken language with us. And I'm not trying to say out there in the everyday land, you know, that the word onto, if somebody says onto and uses it as a preposition, I'm not going to go up to them and say, you're wrong. That's not how we use it in math, right? Like, that's not, I mean, I speak using the word onto as a preposition out in everyday language. When I'm in math mode, if I'm between the dollar signs, oh my goodness, did I really say that? Then I use this word as an adjective. So please be careful. Do not say f of A is injective. Or surjective, I guess is the word. Okay. You can't say f of A is surjective because f of A, remember, is an element of capital B, right? So you can say f is surjective. So this goes back to that warning earlier. Question came up. Sorry, I'm going to read it on this screen. Isn't this saying that the codomain of the function is equal to the range? That is a very good summary of what is going on here. So it's saying, so back when we looked at the way functions were originally defined on Monday and reviewed at the beginning of class Tuesday and today, the codomain is sort of this promise that every output is a member of this thing called the codomain. And now, if you have a function that is surjective, what's going on is everything in the codomain, right? So let me use a new color. Everything that's in the codomain truly has a certain input that effectively realizes that gets you there. Like, so this is really in the end ultimately saying that the codomain of the function is equal to the range, exactly as the wording of the question is. Oh, and I didn't give credit for some of the other things earlier. Chris was the one who had said, I think I saw this in linear algebra, and Lindsay had mentioned horizontal line tests. So all of the comments that have come up so far, like these are all completely accurate. So this point of isn't the codomain equal to the range if you've got a surjective function, that could literally be proved, right? So the codomain is a set, the range is a set, so you could prove these two sets are equal by doing two subset proofs, and it's worth doing. And we're not going to do that right now, but that will probably be part of a future homework. In fact, that's why. Think about how to negate this. I've got it in, in symbols in my notes. Let's just do it, right? So to negate the for all part, you got to have there exists B in capital B. You got to negate that there exists A. So for all A and A, and then you got to negate f of A equals B. Well, that's f of A is not equal to B. So this boxed text here is what it means for a function to be not surjective, and so I think what we should do is look at an example and a non-example, right? So example f set 1, 2, 3, 4 codomain 5, 6, 7 defined by f is equal to the following set of ordered pairs. So ordered pair 1, 5, ordered pair 2, 6, ordered pair 3, 7, ordered pair 4, 5. That's what I think I see in my notes. This is surjective. So what I'm asking you to just verify for a moment is this for all things in B? In other words, do 5, 6, and 7 all appear as an output, right? You see here, this is f of A equals B. There exists an input, so that f of that input ends up being the output. So do you see 5, 6, and 7 always, all of them appear as a second coordinate of an ordered pair? And we do. So then I'm going to just pause for a second, and then, I know in my PDF that I'm staring at, which I've uploaded to Canvas, if you want to look, you can see my non-example, but I already told you what's the key feature to look for in making an example. So why don't I just wait for a minute and have you come up with your own non-example? Maybe even use the same domain and codomain, but then change up this part over here. So can you make a non-example, and then I'll let you know what my non-example was as well. Give you a moment to try that. Scroll. Okay, I'm going to show you my non-example. So I use the same letter, little f. I hope that's okay. Sorry. I'm using the same domain and codomain I used in the previous example for my non-example. But you heard kind of the key, at least in an informal way, the key thing that needed to happen to have surjective or surjectivity, if we make it more into a noun. And it was that every single one of these, the 5, 6, and 7, where the blue arrows are still pointing, every single one of those had to end up as a second coordinate. So as long as that property fails, you should be okay. Here's the example that I have as an example of a function that is not surjective. So I had ordered pair 1, 5, ordered pair 2, 7. There's many other examples other than the one I'm making. Ordered pair 2, 7, ordered pair 3, 7, ordered pair 4, 5. So you'll notice here, 6 never made it as an output. But there's many other examples. You can make a plain, boring example where all 4 of the inputs have literally the same output. Maybe all 4 of them have the output 6. And then 5 is never an output, and 7 is never an output. So is everything in the codomain really making it as an actual output of the function? That's what surjective is about. Same general habit. When thinking about f surjective, It's fine if you prefer to call it f is onto or vice versa, but don't just go in this infinite loop back and forth. Oh, f is surjective means f is onto means f is surjective. You got to bring up at some point. You've got to bring up. Sorry to scroll back and do this. You got to bring up this kind of text, right? So I'm copy pasting it down here. Normally I would just point. That would have been soon enough that we would have still had it on the board in class. At some point, you've got to go that way. You know what I mean? You got to bring up this kind of text at some point if you're going to do anything meaningful, proofs, or come up with your own example or non-example. And the now note or comment I'll make is while the range of f is always a subset of the codomain of f. So even right here, like I know I'm starting one comment. So the range of f is always a subset of the codomain of f. That's this statement underlined in green. You should try proving it at home. Prove it, right? It's a very short proof. It's like a half line. Okay. But I'm going to actually introduce another comment within this process. I'm going to contrast this and say, actually, in addition to this, here's a theorem. To make things a little clearer, let's have a function where we've named the domain and codomain, a and b. Then it turns out that the range, this was the comment that really came up earlier, right? The range of f is equal to the codomain b if and only if f is onto, or you can replace the word onto with surjective if you want. So even this theorem, think about proving this. Try that at home. Hope the only place you are is home. But it's an if and only if, so you got to prove one thing implies the other implies the first. Even here, whether you assume this because you're assuming this to prove that, or you're assuming this to prove that. This equality is two sets which are equal. So by definition, these are two subsets. I mean, there's actually a surprising amount of the proofs are all super short. I don't think you'll get stuck, but there's a lot of good little review of things, and just be very methodical about the process. Stick to what really, really just needs to be happening, and I think things will go okay. I should make the comment with this warning, as I see in my notes. There's a good reminder. Do not say the definition of onto or surjective is that the range of f is equal to b. That's not the definition. The definition is this text. So I'll paste that below again here. So definition of, let me put this in blue. Definition of onto or surjective should turn into text that looks like that. The point is, what we have in this red box over here is another, it's like another view of it, but the point is, this text that's in red, it is logically equivalent, right? It ends up always happening at the same time because of the if and only if you prove the theorem, But the point is, one thing had to be the original, right? The original text was about everything in the codomain has a thing in the domain, so that f of the thing in the domain ends up being the thing in the codomain. There's got to be something that was the original. The original recipe here, right? You don't want to something has to come first. Otherwise you create this weird, each thing relies on the other, and there's a circular reasoning going on. So this thing over here, this thing that happens to be true if and only if f is onto, this thing is, when something happens as an if and only if, it is known informally as a characterization. And characterizations are super useful to think about, because one thing can replace another in a part of a proof if it's helpful to you, but still something has to be the original definition thing. Okay, we're so close to done for today, unless there's any questions so far. Question, Rafi. So a surjective function f from a to b requires cardinality of a to be greater than or equal to cardinality of b. Yeah. In an informal sense, yes, absolutely. That's yeah. You got to have more things in the domain if you're going to have a fighting chance of covering all the things that are in the codomain, right? Everybody cool with what's being suggested here? Now, just because the cardinality of the domain is greater than or equal to the cardinality of the codomain, that doesn't automatically make a function surjective, right? But like, if you didn't at least have that property that is being mentioned, then you don't have a fighting chance of having a surjective function. Nice comment. Cool. These are really neat contributions coming up today. Okay. Last thing, I promised there was only 2 definitions, but I sort of lied. This one's not bad, I promise. The definition here is a function f. I don't even need to mention for this definition the domain and codomain. You could if you want. You could put a colon, a arrow b, or x arrow y, or d arrow c, or whatever. But you don't need it for this definition, so why include it? Let's be lazier if it's possible to. The previous definitions of injective and surjective, you needed to refer to them because when you quantify, you got to say what set the placeholder variable comes from. But this definition is bijective, so a function f is bijective, or one-to-one correspondence. Actually, it's technically, grammatically, it's or is a one-to-one correspondence if f is injective and surjective. That's the definition. Of course, I could have replaced, so the underlined things, either of the 2 underlined things in black are the new terminologies. Obviously, bijective is way shorter to write than one-to-one correspondence. I personally am not a fan of the phrase one-to-one correspondence, not only because of its length, but because how come the phrase one-to-one from earlier appears, but the phrase onto doesn't, right? And of course, over here, underlined in green, injective, surjective, you could replace those with one-to-one and onto if you want. The other funky thing about this, so it's not much of a definition other than both of our previous concepts happen, right? But the other funky thing, and I only noticed this last semester when I was teaching 225, somebody brought up, wait a second, so bijective is an adjective, but one-to-one correspondence is a noun. That's just kind of strange, but that's what it is. So we'll end with that. You'll notice I have one other thing I wanted to talk about today, but it's better to wait, and we'll do that tomorrow. The page 4 of the PDF talks about composition, but we'll wait on that. Questions, thoughts? I'm done with what I want to say, but I will stop the recording, take a question if you have it. Well, I won't stop the recording. See if somebody's got a question. We're done. Okay, see you tomorrow. I'll stop the recording.